Hello. So far we have learned how to calculate characteristic function or moment generating function from the PDF. So if you have fx of x, you can multiply it by e to the power j omega x and then integrate it from minus infinity to plus infinity, and then this gives you characteristic function of x at omega. Now we want to know if we can calculate this one back from that. So basically this is the inverse Fourier transform, but we have to replace omega by minus omega first and then calculate the other one. So basically you can do the inverse Fourier transform, but the only consideration is that omega should be minus omega. So if you do that, the PDF is calculated using this expression very quickly. So you see that characteristic function and the PDF, they are related to each other one by one. The same is applicable with moment generating function by virtue of the Laplace transform. Now, what else I want to learn here is that, as example, moment generating function is mean of e to the power of sx. Okay, so this is equal to phi x of s. Now, if from this expression, if I calculate the derivative of these functions, suppose that I have this function, this expression is whatever function. If I calculate the derivative of this function n times with respect to x, what I could do, if I apply this one, because this is an expectation, the differentiation, expectation here is an integration, an integral. And integral and differentiation are both linear operations, so you could change the order. So this differentiation, if I apply here, phi x of x is equal to this integral. This is equal to this integral. Now, if I apply this differentiation n times, this integration here is a linear operation. Differentiation, each of the differentiation is a linear operator. So I could change the order of integral and differentiation. So what happens is that this differentiation could go inside the integral. So I have integral from minus infinity to plus infinity of d to ds n times e to the power of sx fx of x and then dx. Now this guy is not a function of s, so this differentiation only applies to this function. Now if you take derivative of e to the power of sx, d to ds of e to the power of sx, it gives you x e to the power of sx. So each time you apply differentiation, you get one extra s there here. So this guy is equal to x to the power of n e to the power of sx fx of x dx. So basically this is equal to mean of x to the power of n is e to the power of sx, and that's it. So the summary is here. So so this is the summary of this discussion, this expression. So if you take derivative of the moment generating function n times, you can you get this expression inside this green box. Now basically you can, once you get the derivative n times, you can replace s by 0 to eliminate this part, to eliminate this e to the power of sx. Okay, so this equation simplifies to this one. So if I replace s by 0, I get this expression. So using the moment generating function, so if I have MGF, I can calculate its derivative n times with respect to s, and then substitute s by 0. Then I get moment generating function of x with order of n. So basically, by differentiating moment generating function, I could get the moments of my random variable one by one. For example, if you expand this guy into a Taylor series function of these in terms of s, you could get this expression. This is because e to the power of a is equal to 1 plus a to the power of 2 divided by 2 factorial plus etc., which is equal to summation of a to the power of k, or a to the power of n, divided by n factorial. So I could replace a by sx. So what I get here, I replace this by sx. I replace this one by sx. And here I get sx to the power of 2, etc. And then here I get sx to the power of n, and n is from 0 to plus infinity. If I get expected value both sides, this side will become phi x of s, okay, and the other side, if I get expected value, this one will give me, so I get phi x of s is equal to summation over n equal 0 to plus infinity, and mean of s to the power of n x to the power of n divided by n factorial. So this s is constant, come out of the expected value, and then I get this expression, because mean of x to the power of n is this one. So this expression says that the Taylor series expansion of x about s equals 0 gives this one. So this means that the Taylor series coefficients of the moment generating function are your moments of order n. So this is why we call this moment generating function, because it's Taylor series coefficient, which is obtained using the method in this box, okay, which is obtained using this expression. Take n times derivative and you can calculate it. So this coefficient, or use the Taylor series expansion. So the coefficients are mxn divided by n factorial. So let us have one example. Consider a gamma distribution. Gamma distribution, we have seen that is a non-negative distribution. So here you have 0, and then you have a function like that. So it has an exponential term which decays exponentially, and then you have a polynomial term which is here. So about 0, this is your function. So around 0, your function is about x to the power of b minus 1 times this constant. And after that, these exponential terms becomes dominants and will make your function to decay fast. So abbreviating this one by gamma, we call it gamma distribution because the integral of this function is called gamma integral. So if you want to calculate phi x of s, this is mean of e to the power of sx, and is equal to integral from minus infinity to plus infinity. From minus infinity to 0, your PDF is 0, so I start from 0 to plus infinity of e to the power of sx f x of x dx. Now, this function is this integral. So if I put these two functions together and absorb them together, the constant guy comes out of integral, and these two guys produces this one. And then using the gamma integral, you could calculate easily. This is exercise. If you do that, then things becomes easier for you. And then if you simplify, you could see that this gives you another gamma factor, and then these two guys simplify, and then you get this one. So the moment generating function here, phi x of s, here is c divided by c minus s to the power of b. So something that I want to check if this answer is correct or not, I know that phi x of 0 always is equal to mean of e to the power of 0 times x. Remember that this guy is s, okay? So this is this guy. So the mean of e to the power of 1, e to the power of 0, which is 1, so this shall be equal 1. So if I put s equals 0, I should get 1. And it seems that my check it validates that this answer is likely to be correct. So now you could calculate derivative of this with respect to s n times and replace s by 0, and then quickly get the moments of x to the power of n. Because each time you take derivative of these, you will get 1b, and this b becomes b minus 1. Okay, so you could check that. So you can calculate 1 times, 2nd times, 3rd times, and n times. You can get the formula. So the moments of gamma distribution can be quickly calculated using differentiation here rather than integration. So this means that mean of x is equal to b over c, and mean of x2 is equal to that, and the variance is equal to this guy minus the square root of this one. So sigma 2x is equal to b times b plus 1 divided by c2 minus b divided by c to the power of 2. If you simplify, you get this one. Something else you may want to do is to get ln of this one and expand the logarithm of these in terms of Taylor series expansion, so which can give you the mean and variance differently. One example of this case is where b is equal to 1. So this will become exponential distribution, and in that case this guy simplifies to this one, and the mean is given by that and variance given. Remember that here gamma distribution b doesn't need to be integer, doesn't need to be even bigger than 1. It could be 1/2 or so on, which in many applications happens. Another example is that suppose that in this example b equal to m over 2 and c is equal to 1 over 2. This case of gamma distribution becomes chi-squared distribution. Chi-squared distribution is a very specific example of gamma distribution, is denoted by that. The importance of this is in a statistic, people they use it often. In that case, your moment generating function simplifies to that, and mean is equal to this, variance is equal to this one.